En el turno de preguntas de esperar el micrófono, porque si no, no sale en la grabación. Gracias.
It's a pleasure to introduce Tom. To some of us, he doesn't need any introduction, of course, but obviously many of you younger people will need to know a little bit more about him. Tom is a specialist in the early universe. I think that means he gets up at about 6 in the morning. but anyway, he did his thesis in München, and it was about the formation of the first stars, how stars form in general, but how the first stars form. And then he got interested in the subject of the reionization of the universe. And I hope he'll explain to us a little bit about that. And he, from having done his PhD in Germany, he very nearly did it here. He nearly came here to do his PhD, but eventually he returned to Germany to do it. He spent a couple of months here in 1995. And since then he went to Cambridge, UK. He was in Illinois doing postdocs. He then went to finally settle in Stanford. No, he was in Penn State for about 3 years, I think. Mm-hmm. And then he went to Stanford, where he is now, Stanford University, to the Kavli Institute, and he's their associate professor. And his specialities, apart from those things I've mentioned, are the systems of lines in quasar spectra, the formation of supermassive black holes, magnetic fields in galaxies. The advantage of doing the early universe, of course, is that nobody can really test what you predict, and but he's since showed himself to be an honest man and has started predicting things that we can actually observe. Well, I've talked long enough. Here you are. Welcome, Tom.
Great. Thanks. Thanks so much. Thanks all for coming. What I'd like to do today is tell you mostly about sort of a program I've been involved in the last 15 years or so, trying to understand galaxies as ab initio as you can. So we're trying to, in a way, really just go from the Big Bang to the observed universe today in as realistic fashion as we possibly can. I'll tell you a little bit about that. So most of the work I'll discuss today is, let's see whether this works. Yeah, maybe a little bit. Actually, was done in my group at Stanford, and so the names that you see there: John Wise, Peng Wang, Chiung Kim, Mr. Alvarez, and Med Turk, were either former students or former postdocs with me. And in an outline here, I'll tell you about some basic things about cosmology that most of you will know already. Then discuss a few things where first stars originate. And some of the interesting things we learned is that they seem to be quite massive, and that by itself has a lot of interesting implications. The ultraviolet radiation that comes out, the heavy elements that comes out from them. And I'll show you some attempts that we have of putting this all together into a picture of really how early galaxies form, and do this one star at a time, really sort of trying to follow every single star in the model, how these galaxies come about. But then I also hope to have some time to chat to you about that's the origin of magnetic fields and amplification of magnetic fields that we know to be so important in our own galaxy, already in the interstellar medium, but even more so in the cold medium, cold neutral medium, where the magnetic field can provide a significant source of pressure is dynamically important. And of course, if you were a cosmic ray, you'd be much more interested in magnetic fields than as a human being yet. But anyhow, so we'll chat a little bit about that, and this will inform us then, where I'll show you a few numerical experiments where we try to run experiments on a computer, where on the computer we change the conditions to try to elucidate a little bit the important processes going on in star-forming regions. And in particular, I'm curious about why star formation is quite slow. So in some sense, the whole theme of the talk today is I'll walk you through a whole bunch of numerical calculations, ways of how we gain intuition, playing God, if you want, on the computer, trying out different ways, and some of the insights we've gained from that, and where we stand in making the most realistic model of galaxy formation that one can. Okay, so that's the plan for that. In a nutshell, this just sums it up. What we're trying to do is we go from the upper left corner, the cosmic microwave background radiation, to the bottom right, you might recognize as the LMC, to get an understanding of this 13.7 billion years of history of our universe, in how it made structure, in how it made galaxies, how the large-scale structure of the universe came together. And our questions become more and more detailed as we go on. What sets the colors? What sets the shapes of galaxies? What sets the different correlations we observe between the supermassive black holes and the bulges and the disks, the metallicity and the mass and the velocity, and you've seen so many of them. But in some sense, if you think about physical cosmology, of what we're trying to do, is really quite crazy, because we're trying to understand everything. That's where you can find. So we're really trying to look for any causal connections to the state of the universe and galaxies in star-forming regions today in cosmic history. So that's ultimate job security, right? So we'll always have another question to ask. That's a good thing. But it's also a beautiful license for us to sort of think about many deep questions in cosmology. On the one hand, though, actually, let me just say again, if you look sort of at the beautiful data we now have on the cosmic microwave background radiation, we have such a wonderful idea of what the universe looked like 400,000 years after the Big Bang. It's just completely remarkable. In particular, we're sort of very fortunate that it's a very simple state. I mean, it's like it's just boring, right? Not the science. The state, what it looks like, right? It's completely homogeneous. You have 1 part in 1,000 fluctuations in density, 1 part in 100,000 in temperature. I mean, it's just completely super simple, homogeneous, same thing everywhere, right? It's just completely remarkable. And that's, of course, why it's easy to describe it. And for us, we're lucky that it's that simple, because we can linearize all the equations that describe the state of how matter is moving back then. Right? So we don't have to do enormous supercomputer calculations to analyze cosmic microwave background calculations. All we do is we take the hydrodynamic equations, we couple it with the photon fluid, and then we linearize over the mean state, and then can do all the analysis in linear terms. So everything can be done analytically. There's a couple of things that are a little bit more complicated that have to do with recombination and how the actual states of the hydrogen atom, etc. But in principle, the analysis in that sense is quite easy. And the beautiful thing is we can describe that state as a homogeneous density and temperature, and then all the fluctuations on top of it are in some sense the simplest ones you can imagine. Right? As far as we know, they distributed as a Gaussian random field in density, and it's perfectly described by one function, the power spectrum. So, and that just tells you the typical variation at any given scale in density. Right? So it's one function, the power spectrum, the number of, what's the temperature at recombination if you want, what's the density. And we already described the entire initial conditions of the universe. Almost. There's a little bit more in that the velocities are also folded in. But now the beauty is the velocities are completely consistent with that the universe used to be completely homogeneous, and the density fluctuations you have now are only resulting from material having moved towards the regions of higher density, moved away from in the regions of slightly lower density. So again, the velocities are actually completely correlated directly with the density. Anyhow, okay, it's simple. Right? I mean, cosmologists generally make it sound like very complicated, power spectrum here and, CL, this and that. In reality, it's extraordinarily the simplest state you could possibly sort of imagine. That's different yet from homogeneous. Okay, maybe a white noise spectrum would have been yet easier, but anyhow, the amazing thing is that we actually see this directly. There's no speculation anymore. We beautifully probe this, and we can just from those observations alone, but of course it gets much more powerful when we fold it together with other observations, whether it be supernovae, clusters, the large-scale structure of the universe, probed by either lensing, galaxy surveys, and the like, that's very strong. But the remarkable thing also is that if you only take the cosmic microwave background alone, you already can infer an enormous number of things. You get a good sense about the geometry of the universe, the location of the first peak. You get a sense about the distribution of dark matter versus regular matter. Now even you get some sense already that the regular matter wasn't just hydrogen, but also part helium. All these things you can infer currently with the data we have already from the CMB alone. All I'm saying is that this is a wonderful place to work from. And so for a physicist, I like to sort of check that structure formation and how we come about it, in principle, is an initial value problem, right? Because if you know all the equations, whether it be gravity, hydrodynamics, chemistry, perhaps how radiation works, you put this all together with the cosmic microwave background data and the inferred state of the universe, you actually have your starting point. So you know the initial value, everything, everywhere in the universe, in a statistical sense. Okay. All right? But you know that, and then you should just be able to evolve it forward in time. Right? So if you had all the correct, proper equations, that's it. You've got initial conditions, and you just evolve forward in time, and then what should come out should fit exactly what you observe. So, very simple. Right. Now, the only thing, of course, is that it is the whole universe. So we definitely, won't be able to do it on a sheet of paper. So you're allowed to use a computer in the homework problem to solve the equations correctly. And the tricky bit here, usually what comes in, is that we also just have this crazy range of scales. You think about, our sun being 1 trillion times smaller than the Milky Way, and you just think about the densities that you have. So the central density is of 100 grams per cubic centimeter. That's, what is it, 26? That's 34 orders of magnitude denser, the center of the sun, than the mean density of baryons, of gas, in the universe. So 34, let's call it 33 orders of magnitude. Because when we take the third root of this, it tells us that the material that's in the sun now, even if it was a complete spherical cow that just slowly contracted spherically, that it used to be 10 to the 11 times larger, right, when it formed. So that's a 10th galaxy. So it's an enormous region, actually, where all that material came from that sort of made it into the sun. And you should, and I usually like to sort of think about that because that's also true for, of course, all the atoms in your body. So in some sense, if you just query every single atom, what was the farthest place you've ever been to, you should get something of order tens to even 100 of kiloparsecs. Okay, so we used to be huge. Anyhow, well, I'm getting bigger, but not that big. So that's just the spatial scale. But similarly, of course, the time scales also have this enormous dynamic range. Like things here move very rapidly, and also if you think about the surface of the sun, say a typical thing moves where you watch your convective cells. You hopefully do it from here. Terry, feel like these times you really go down to minute timescales. Whereas if you sort of think about the rotation timescale of the galaxy, like 250 million years for where the sun is, it's again of order sort of trillions in differences in the timescale to consider. And so that's in some sense always the trouble with doing these calculations. And we've been fortunate to put together numerical techniques that use what we call it, or what's called adaptive mesh refinement in order these problems, so that we can do calculations that may have an entire galaxy contained in it, but we still can zoom in and focus on the formation of an individual star in that. So the way this goes is, the key physics that you want to include are just you solve conservation equations. Okay, as material moves around, there's a mass conservation. You want to conserve the mass in your calculation. You want to conserve the momentum, you want to conserve the energy. And so all we're doing is we solve this system of what's usually called the Euler equations, it's the inviscid fluid equation. And then more recently, in the last few years, even in these cosmological calculations and also galaxy formation calculations, we include the effects of magnetic field in the limit of describing them in the ideal MHD limits of magnetohydrodynamics. To simplify a little bit, but all that means is you take a big part of space that you're trying to model. You think of it, you have a computational grid, so all that is an array of values. X, Y, Z components tell you the density, the internal energy or temperature if you want, the velocities at that position. Then you might have the magnetic field deposition. Then you want to record things like the chemical composition, how much hydrogen, how much helium, how much of it is in protons, what is electrons, how many carbon atoms do I have, is there carbon in CO, and so on. So there's a big complexity there in the chemical space, if you want. And so you sort of split up space, but you've got these attributes for every single cell on your computational grid. It records also the mass or the density. It's connected because you divided it up in small volumes. Now, but as we said, as the sun forms, it collapses, say, 11 orders of magnitude in radius. You now, if you want to do that in one computational grid, you would have to make sure that you have 10 to the 11 zones in one direction and in the other direction and in the third direction. And you can barely fit 10 to the 11 zones just one-dimensionally on a computer. So that's not working. But what you can do is you start with a three-dimensional grid, say, with 1 million points in it. And as things move closer towards the center, as you picture, you now introduce a new grid there where you interpolate the values from the top. You just say, okay, I have this functional form, but I want more resolution here. So I add more interpolation points at that point. As it gets sharper, you add even more points to always be able to describe that function correctly. So you do this in 3 dimensions. You do it recursively. This way you can have, we now have hundreds of thousands of these grid patches, call them, the little bits of grids. They all have and they just nested. And so we can have them 40 levels, 50 levels. And so at some point you may end up with a cell that's 10 to the 15 times smaller than the overall simulation volume. So with that we get the dynamic range that's required to actually represent a star, say, in a galaxy. But fortunately, we also can do this because the hydrodynamic equations are quite local. You can actually, you know exactly how far and how fast information can travel because it's just the sound speed, right? Just like you're listening to me, so there's a very clear, sound travel time it takes for the sound waves to travel to your ear. We know this in the hydrodynamics, and as a consequence, you can solve these hyperbolic equations in a way where you just update small regions many times, in larger regions less frequently. As long as you make sure that how the mass, momentum, and energy couples, and you have this hierarchy of timescales, you solve the equations perfectly. Okay? So that's a huge speed up. That allows for some of these calculations that would be otherwise completely impossible if you had to evolve everything at the same time set. So as I'm speaking, we have some hertz, I don't know, so we need tens of thousands, let's say 10,000 updates per second to get the sound waves that I'm producing. If I now have to evolve in all the stars in the Milky Way 10,000 times a second, just move them. They of course don't move, but every time I would calculate the minuscule amount they actually move, there would be a lot of calculation wasted. And that's essentially what we avoid in adaptive mesh refinement, by being adaptive in space and also in time. Okay, that was a little longer than I thought. Anyhow, that's sort of the way you can do this. And here's sort of a particular example where we started out. I show a gas density in the top left, H2 fraction here at the bottom. So that's molecular hydrogen, and here's the temperature. It comes out a little bit dark on here, but what you notice is we keep zooming in, and we put in those little boxes here that tell you what the current scale is. So here we're at 5 parsecs. At the moment, you see a cold region in this particular case. It's a few hundred Kelvin cold. So here, now we're down to 1 parsec. The gas density, in some sense, looks very boring. The further we zoom in, it gets denser and denser and denser. There's always one thing that's even denser yet, right in the center. And we're zooming towards that. But in these type of calculations, what we actually do is we start essentially where the cosmic microwave background radiation tells us what it looks like, then evolve forward in time until the very first interesting thing, interesting in the sense that something very small forms in this calculation. What we find is that we make protostars that have 10 Jupiter masses. Very boring, actually, because in some sense all stars, this is universally true, all stars in the galaxy, and it looks like even for the very first one, started as 10 Jupiter mass protostars. The question is only how much did they accrete later on, okay? So even if you find, if at a car or, you look at some amazing stars in the galaxy, they had 50 or 100 solar masses even they started with 10 Jupiter masses and then accreted over time. And typically, it sort of depends how rapidly they accrete, whether they run out of the material or not, of what their final mass is. And we're in a very similar situation in these calculations where we really did all the cosmological stuff. We follow the dark matter, we follow the large-scale structure, evolution of the universe, we sort of see how the gas comes together, we follow how the molecules come together, how they radiate, how the gas then falls further, and we can follow this all the way. Should be roughly. It's only at 10,000 degrees Kelvin at this point, but in the computation, the time step already is less than 2 minutes. But to calculate that time step takes longer than 2 minutes. Okay, so that's real-time computing. But what happens here is we just cannot evolve it further meaningfully. We'd like to see the next 100,000 years of the evolution of how this protostar accretes and becomes bigger and bigger. But it's so many dynamical timescales that not only do we have trouble. It's not that we're just lacking computer time. It's really even the numerical methods we're using would not be useful to take 100 million time steps with a method that doesn't have that accuracy, let alone that we can't afford to take the 100 million time steps. Okay. So anyhow, but the great thing though is we do know a lot more than we did before without doing the calculation, because now we can actually look at all the material around the protostar. And just at that last moment in time that we still could simulate to, look at the state, what is it doing? And we actually see it falling in at tremendous rates. So the accretion rates we get here are of order 10 to the minus 2, 10 to the minus 3 solar masses per year. So within 100,000 years, there's actually no problem getting up to 100 solar masses of material. But what we're very much puzzled by and curious and would like to calculate is how much that protostar, say, when it has 10 or 20 solar mass, when it has 10 or 20 solar masses, how will that act back onto the accretion flow? Will the protostar itself regulate how much mass it'll grow, and from that set the limit on these on the masses of these earliest stars? do we, likely we'll still make disks around these protostars. Can they fragment? If they fragment, do the fragments survive? It's like all these sort of questions that I would like to get to. And, where this whole field is, in fact, of course, quite identical to doing star formation in our own galaxy. The only beautiful thing for the very first stars is that we knew the initial conditions. We actually knew what to start from. And that's something we usually don't have the luxury when we study star formation in our own galaxy. Yes, please. So it's a statistical distribution of this. So the very first star in the observable universe, so the very highest redshift thing you should ever be able to find should be around redshift 70. So, there is one supernova at redshift 70. Is one of the predictions that comes from this. You have to survey the entire sky to a crazy depth, of course, to find it. And you have to be very patient because the light curve is extraordinarily stretched in time. At redshift 70, it's 71 times longer than it usually is. So you have to wait years to see any change in the luminosity. Anyhow, so at redshift 70, we had one supernova, but then of these population 3 stars or stars without heavy elements, you make most of them likely at redshift 30 to 20. But, it's sort of a statistical thing. So it's just like we have, one, 10 to the 9 solar mass black hole in 1 per co-moving gigaparsec at redshift 6 already, right? So, there is some statistically rare places where something started a lot earlier. Like, look at galaxy clusters. Also, very rare places, but quite amazing in that so much material already collected into 10 to the 15 solar mass objects. So, there's this whole distribution. Anyhow, what's remarkable is that, in fact, this whole mass scale of about 100 solar masses or so that we see material being ready to fall onto these protostars, we can actually get purely from molecular physics. Because we look at the temperature that molecular hydrogen can cool to and find it's about 200 Kelvin. And that's just because there is the lowest lying rotational state is at 512 Kelvin excitation temperature. So to get a hydrogen molecule to rotate, the neutral hydrogen atom that it's colliding with has to have that energy to get that lowest lying rotational state going, 512 Kelvin. Now, since there is a Maxwellian distribution of velocities, you can cool even when you're at 200 Kelvin. There's still a few hydrogen atoms that move fast enough that they impact at 512 Kelvin onto the molecular hydrogen. It starts rotating, gives off this quantum, so it stops rotating, but a photon leaves the cloud. And that was the cooling that allowed all this dissipation, right? Because when material, of course, falls under its own gravity, as it falls, it would get hotter and hotter, right? It gains all this potential energy, right? So, in other words, it normally would be flying faster and faster and faster because it's a gas, it starts running into itself and it turns the kinetic energy into internal energy and it heats up. So you need this dissipation, like have radiation be lost so it can continue to collapse. And you have to really do this for a long time. And it's amazing when you actually go through the numbers of how much radiation is released. It's an enormous amount of energy that you have to release just to make a star. Problem is you do it over a relatively long time scale, and but I mean, as many of you will know that all the luminosity of young protostars is purely driven by accretion luminosity, right? It's its own gravitational energy. Even though the star may already be burning hydrogen in the center, that has nothing to do with the luminosity that actually comes out. It's quite interesting. But we'd like to do more on this. But what we find, just having high temperatures, we get very high accretion rates, which argues for having quite massive stars. Likely somewhere between 30 and 300 solar masses, and and likely there's a distribution depending on statistical issues of exactly which object you're looking at, how much angular momentum does it have, does it make a disk, what kind of disk, does it first make a disk like this, then another one like that, of course it would be a zoo just like we see the zoos of star-forming regions in our galaxy. However, that they are massive and that most of that mass will go into massive stars is, our best understanding, what we can also gather from these calculations. And that has an enormous number, of course, of implications. I mean, even in some case, we already now see as the material collapses, in some we have enough angular momentum that it already breaks up into binaries or multiples. We've seen triple systems as well. And as you imagine evolving this whole thing further, it's likely you'll get more multiple systems for these early objects as well. But having these massive stars as being the outcome, you already know one thing right away. They will produce a lot of ultraviolet radiation. And in fact, kind of interesting, I mean, we don't know the exact mass, as I explained, but if we do a few different ones here, so from 30 solar masses, 40 solar masses, all the way up to 100 solar massive at the bottom right, these calculations here just show you in about a kiloparsec or so, a little bit larger than a kiloparsec, the temperature in a full radiation hydrodynamical calculation, where at the very center of these filaments here, I made a star. It's a kiloparsec box, okay? This is a lot larger than the star. So we're thousands of light years instead of thousands in scale. And you see the 30 solar mass star would live a lot longer than the 100 solar mass star would. But the 100 solar mass star starts out quite more luminous. So it ends up ionizing quicker the region around it. Okay, so this is all photoionization. UV light comes out, splits the electron and the proton off the neutral hydrogen atom. And the electron carries off the excess energy, of course, of the ultraviolet photon, heating the gas. And that's why you see the temperature rise so dramatic. And there's very characteristic shapes to this. We have filaments sort of draining in. We often call it a butterfly shape here because the radiation tends to escape into the void that's between the galaxies at the time quicker than it does along the filaments. What's remarkable about this is it's such small objects where these first stars form in. The total mass of the dark matter halo that contains one of these first stars is less than 10 to the 6 solar masses, so a million. So the mass of a globular cluster, right? But its typical region or radius is about 100 parsec. So that's like 50 times, 100 times larger than a globular cluster. So the escape velocities are very low from these objects. So all you do is, like, once you have a star and it heats the gas around it, that gas, just by having a temperature of 10,000 or 20,000 Kelvin, is so hot that it will overcome the gravitational force that kept it in the galaxy or in the dark matter halo. The gas will run out and escape at about 10 times the escape velocity. So go out at 20, 30 kilometers a second. So if the star now dies and you make a black hole, say, it finds itself completely evacuated. It just sits there, and all the gas that used to be around it ran out. So these very first black holes would, in fact, not grow very much because they find themselves in low-density regions. But there's another consequence here that once you, if the star now, because it's massive, it had all this UV, evacuated all the region around it, if it now goes supernova, the heavy elements that were made inside the star would actually be able to get quite far because there's not much things it has to push through. So, in fact, whether I have a very strong supernova or not such a strong supernova, we sometimes even talk about these crazy parent stability supernovae, which could have 100 times the kinetic energy, in the most extreme case, than a regular type 2 supernova today. And they're, of course, very energetic, and you'd think, oh my God, they will throw the heavy elements everywhere. In fact, even if it's a weak supernova, you still get the heavy elements quite far because radiation already did much of the clearing. And so there's a shell of material that's already running ahead, and now your supernova ejecta have it easy to catch up with that material. Here's sort of a more beautiful rendering. So you see one of these stars form at the bottom right here, and you see these pillars get shaped very much like, you've seen this in H2 regions in the galaxy, as photographed by Hubble, say. And here you have got a supernova remnant expanding. all this material just coming out right here. And what you notice is with all these beautiful pillars that the star actually shaped, as the star dies and the source of photons dies out, all the pillars actually photoevaporate. So they essentially explode, and that's because you set up a photoevaporative flow off the pillars, which now when the star dies will very quickly just drain all this material out. It's like some of you know this better than others yet. Anyhow, so here's just a spinning a little bit to get a sense of the three-dimensional structures. What we've where we spend a lot of time on is developing these numerical techniques where we can do this radiation transport on these adaptive meshes to do this coupled calculation of how you have a star, radiation comes out, it ionizes material, so radiation gets this far. That means it heats it, which gives a higher pressure. With a higher pressure, it expands the material, makes the density lower, lets the radiation travel further, change the opacity, right? So that's why the radiation gets further. And so you have to couple this whole thing between the chemistry, of what ionizes, between the radiation, what's the opacity, how far does the radiation travel, to how the material moves, and then do this in parallel over tens or even 100,000 of different patches that are at different resolutions. And so we spent some time on it, and that's why we're so proud on little things like this where we can have a shadow of something tiny like that, where there's a small knot that was formed in an instability of the ionization front deep inside the galaxy, and we still sort of see the remnant as it's expanding out towards the end. Yeah, so that's for the technical-minded folks. I mean, we had a lot of fun developing this numerical technique. So here is now trying to take this picture that I showed you for 1 or 2, 3 stars, to sort of do this for many tens to hundreds of stars, and think about how the very first galaxies build up in this picture. So again, what's shown is a density square weighted temperature in a region that's about 7 kiloparsecs across now, so significantly larger. And it's a full sort of cosmological evolution. Again, you make lots of little galaxies, and I use that word loosely now, galaxies just in the sense of a dark matter halo that ever hosted a star. So even if it just has one star, I already call it a galaxy. Anyhow, we never thought about this until a few years ago. Of course, now that we found some galaxies that only have 100 stars in them, it's time now to think about actually what do we want to call a galaxy anyhow. Same thing, of course, is familiar to many of you is like when you look at globular clusters, and now they have lots of populations in them, and we've got to sort out exactly what we best, how we use our terminology. And so here is just any dark matter halo. So dark matter dominated object that ever had a star. Anyhow, so what you sort of notice is that in temperature, you see that with these early stars, it's like fireworks. It goes so fast because their lifetime, maybe say 3 million years. And that's sort of more or less constant for high masses, above 80 solar masses or so. They all live 3 million years. But the typical timescale for this stuff to come together is tens to 100 million of years. That's how the dark matter halo merging occurs on these timescales. And so what you notice is it really is like fireworks where the stars just go off. They just very quick flashes. So this is a period that lasts about 300 million years in the calculation. And you see many of these H2 regions overlapping. And let me just show you also what's underlying here is the gas density is in white and sort of grayscale. And overlaid is the metallicity of the material in color, which goes all the way up to -2 solar metallicity. So in these calculations here, we assumed it's actually parent stability supernovae, that the typical mass of the stars that form in the first generation is about 170 solar masses. And so enrichment is quite quick. If you think that's a bit too much, they only have a few times higher metal yields than a regular type 2 supernova. So you could scale it down by a factor of 5 or so in terms of metallicity, but I think not much less. So that seems to be something robust, actually, that we learned from these calculations, is that we have early enrichment up to a level of 10 to the minus 3 solar metallicity without any problems. It's just completely normal from these early stars, because, you know, you make mostly massive stars. Even if a small fraction of all the gas mass goes into stars, since they're massive, you actually very quickly enrich, right? You don't waste a lot of material in putting it into brown dwarfs. Boring. Okay. But, you know, you know, sometimes in the regular IMF, you end up putting a lot of mass into brown dwarfs, and they then, you know, don't act back on the material. And so in this way, you could hide a lot of baryons and make metal enrichment slower. Absolutely. And right? Yeah, there's already, exactly. So there's already a shell that came from the H2 reagent alone. And the density contrast of that shell becomes less and less because it's not self-gravitating itself, and it's really blowing into very low density material. So the shell is not very well defined, and it's, in that sense, it's not that exciting of that it becomes a full self-gravitating structure that itself then could lead to new stars or so. That doesn't occur at all on these small mass scales. But what does happen is now it's quite porous, and the heavy elements that catch up with the shell later, they mix you know, in this low density material, and many of them do overlap. So it's really not just sort of, you know, that you get the material of one star first expanding, and then, of course, later it falls together again by gravity. It's really many stars that expand, and then it's the collection of them that falls back together into making a larger galaxy. So the typical dwarf galaxies now collect from a few to tens of these early stars. They have the elements, and out of that make the first generation of metal-enriched stars, which, you know, some of them, if we make low-mass stars, which we must, which some of these stars still, of course, hang around in the Milky Way halo. And it's the whole research program of doing, studying the fossil record of these objects, looking at the abundance patterns of halo stars that we try to infer of whether these ab initio predictions are sensible. There's unfortunately always a few more steps that we then have to do. Even if we get the metal enrichment quite right now, and we can follow this, we still have to get correct of how the next generation of stars formed. What is their mass distribution? How many of them are in fact low enough mass stars, sort of less than 0.8 solar masses, that they're still around today? And so there's many steps that sort of go into relating the fossil record or the abundance pattern of a star I see in our galaxy back to what that says about what happened 200 million years after the Big Bang. Sure. Yeah, so for that, I think you need a very solid prediction of exactly how star formation works at low metallicity. So that's a really tricky one. What I can say, though, from what's easier to say from this calculation is that it's hard to find regions where the metallicity is much less than 10 to the minus 3. So I'm, in that sense, from these calculations, now puzzled where true 10 to the minus 4 solar metallicity stars come from. That is not that easy to understand at the moment. You know, and by true, I mean the ones that really complete metal, not just iron, right? Because there's a lot of talk about 10 to the minus 5 and less in iron, but then they actually 10 to the minus 2 or 10 to the minus 3 in total metals. And so that's, you know, that's also very interesting, but I don't think relates as much to here. I'm looking for the regions with the less heavy elements to begin with, to think about the first generation of stars that formed right after the really first generation. Okay. Oh, I'm having fun. Anyhow, these are some of our best attempts now of what some of these galaxies look like. It's getting there. I would say, we're doing hydrodynamics. There's a lot of things, a lot of scales here that we'd like to simulate, but we can't fit on a computer. But what I am seeing sort of over the last decade or so, we now have many hundreds of millions of resolution elements, and you can actually start seeing that difference, that the sort of fluid character is actually recovered. So the numerical Reynolds number is getting halfway reasonable. We're still not capturing turbulence that well in these numerical models. It's turbulent and it's all quite chaotic in that sense. But in terms of turbulence, like you think about in an experiment where you have Reynolds numbers of 1,000 and more before you have the onset, to predict these things in detail, you just can't do that on a computer, and certainly not with this huge range of scales that we have to actually worry about for this. Anyhow, so all I'm saying is, we can do different types of galaxies, look for them in clustered environments, look for other ones that have a different mass accretion history, some that build up slowly, others that merge a lot, and sort of get a sense now of sort of the interplay of these physics of how star formation, the feedback, that all comes together, study the chemical enrichment, the buildup of the metallicity of the stars. And we're also starting this program of trying to compare this with the fossil record, mostly actually looking at dwarf spheroidal galaxies around the Milky Way where we have good data on this. But it's still a long way to go, as you can imagine, because we can simulate in this kind of detail where it's really every single massive star we can simulate the first few 100 million years, maybe 600, 700, 800 million years after the Big Bang, and we can make galaxies up to masses 10 to the 9, maybe 10 to the 10 at the very most, right? The 10 to the 9 solar masses. So we can only probe the smallest one when we go to that level of detail. Right. But it's also exciting because it's also just the time now where ALMA is coming online, where in a few years we'll have JWST. We have all these enormous telescopes now. If you think just of a OWL or the really big telescopes coming, we'll actually get direct measurements of the galaxy population as a whole at these redshifts. 10, right? 8, 10. Crazy. And in some cases, even with this resolution of 100 parsec or so, physical, which will be quite something. So I'm glad we finally got to that stage, at least, that we can do predict things that will be reachable in the near future. Because for a long time, all we could do was make individual stars, and even if they are a million times as bright as the sun, they never were bright enough for us to be able to detect them individually. Okay, so actually, how much should I plan? Maybe 5 more minutes, 10 minutes? What's usual? Okay, all right. Chairman. So now, let me just sort of pick this up. At the same time, this is now a scale that's yet a few hundred times larger. This is 100 co-moving megaparsecs on a side. Where we're trying to model not only handfuls or hundreds of galaxies, but we're trying to model millions of galaxies and their effect on how they ionize the universe. And again, in some sense, it's just a scaled-up version of the things I was talking about, where I had an individual star, and I was concerned with the region around the individual star. I'm now concerned with individual galaxies and the regions around them. But due to the whole large-scale structure of the universe, as you see, here is just a galaxies actually that did all this ionizing. Here's the universe evolving backwards in time. Sorry, let me just say that the dark regions, of course, is where the neutral hydrogen is. In blue, in transparent, is where ionizing radiation made it hot. Blue for an astronomer, and transparent. And so we're witnessing here really this interplay of how galaxies form in the large-scale structure, how do they cluster, and how do their UV photons together make this somewhat complicated morphology in how the hydrogen gets evaporated. There's a lot we'd like to understand here, and of course this is also in preparation for many of experiments coming online, including LOFAR, but also MWA and of course, eventually the square kilometer array that hopes to do actual H1 tomography, where it would be the red regions here, or the red dark regions that we'd be able to sort of slice through observationally, And we're making here numerical models to have predictions for this. So what are the relevant scales you want to look for? Now, there's a number of interesting things one could learn, in particular about the mean free path of photons, about the important constraints, I think, on the ratio of UV photons to optical photons that you could constrain. Would you have these observations and the like? Okay, so I had too much fun at the beginning, so I have to fortunately skip a few things. Just to say, with magnetic fields, since everybody else always neglects them, I'll do the same today, and just use the last few minutes to talk a little bit about star formation now on Milky Way. Because of many of the numerical techniques, of course, that we're developing, it's just suited for astrophysical fluid dynamics. So we have been doing applications for neutron stars, believe it or not, with really kilometer scales, all the way, of course, to the large scale structure of the universe. In this particular case, I wanted to focus more on parsec type scales, and know a little bit about how come star formation is so slow. Here are just some of my favorites, sort of the LMC and the Spitzer image, just showing how much gas there really is. And the Phosphor Nebula is a prime example of, and many of you know this for Taurus and many other regions. Oh. Sometimes. So, anyway, this one, I don't know, but where did it go? Here's a corner. I don't know. Anyhow, that's a Phosphor Nebula, and you see sort of in the middle going through all the filamentary structure. And if I encourage you to look at that on your own screen, not on these projectors. This very fine wispy filaments that you've seen in so many objects now. Also, just recent images from WISE come to mind, and of course in Herschel as well. That it's just so clear that magnetic fields play a very important role in shaping the structure of these things. It's very often people like to sort of try to neglect it, but every time we have a measurement, you just by eye you look at it and you say, oh, that doesn't look very turbulent or messed up. It's sort of nicely filamentary. Every time people can go and measure magnetic field direction and values, it's always aligned exactly, how you would have imagined it. Anyhow, so can't neglect them. And I think essentially what I want to tell you about today is numerical experiments where we find the magnetic field to actually have a rather interesting role to play, in that the large component of the field that threads molecular clouds in our Milky Way and in other galaxies, that it all plays this perfect role of coupling any feedback you put into the cloud or any momentum you put in. The field lines that thread large regions of the cloud can actually couple any energy injection or momentum injection you have locally to a large region in the object. And to show this, do is a very simple numerical experiment. So I have a little cloud. Okay, it's round, has isothermal distribution. That means the density outside is lower than in the inside. A few different experiments. Okay, so I just say, okay, isothermal cloud, and I only give it. Let's see. Here, sorry, wrong direction. Yeah, that'll work better. So I'll take this round cloud, and I just say, okay, so it's static, but then I put in a velocity field that it's moving at a Mach number of 10, just like it's observed from molecular clouds. So it gets a velocity spectrum imprinted, and that's what I call turbulence. And I put in as much energy in that so that it's virial. That means its gravitational potential energy is balanced by the kinetic energy in the turbulence. But it's Mach 10, so that means the kinetic energy is much more than the internal thermal energy. Okay? And then I don't assume any magnetic fields and no proto-stellar outflows. The next one, I'll also add a magnetic field consistent with the observed value for something this dense that we started with, of almost 10 to the 4 particles per cubic centimeter. And still no effects of stars. And then I also add contributions of, when I have stars and I make a small protostars, I'll give them protostellar outflows exactly like we observe them. So I give them the momentum that's observed of protostellar outflows, and I have an efficiency that, again, matches observation. Okay, and it's just a simple numerical experiment. I want to compare these different approaches. In one case, I still have the protostellar outflows, but I take away the magnetic field. And what's been really fun with these calculations is that they have a number of properties in being star-forming regions that work much better with the observed values than any previous simulation. And the simplest way I can explain it is just with this one diagram. They have a total stellar mass here as a function of time. And so this first model, which was a sphere that started out static, had no turbulence, nothing, just a sphere, under its own influence of gravity. Okay, whoop, after one dynamical time, just collapses exponentially. Good. There's a slight turn here for a keen eye, and that's because I had a nice thermal density distribution, so the mean freefall time gets longer and longer. So that's why it's not totally exponential. But now I add some turbulence. Well, it takes twice as long. That's a well-known result, where we had also about 15 years now, that supersonic turbulence damps on a crossing time scale. So it takes one crossing time before it dies out, and after that, it again exponentially collapses. If I add a magnetic field, I get a little bit more. So it takes a little bit longer, but again, the cloud just collapses away exponentially. So initially, because you now can only move along the magnetic field line and not so good perpendicularly, you constrain the cloud. But once it gets going, your cloud will get smaller and smaller and smaller and just go on its free fall time. But the remarkable thing was, as soon as we have protostellar outflows, you get into the self-regulated state where over time, you see it just constant, makes stars at a constant rate. Right? It's just a linear relation on a linear plot. Just makes stars at a constant rate. And the way that works is if the cloud contracts a little more, the stars will accrete more material because it's sort of denser, right? So also more material is accreted on the protostars, which means they have more protostellar outflows. So that gives momentum back, which now couples through the magnetic field to expanding the mean density of the cloud, slowing the accretion rate. If you expand too much, then density goes down, less accretion onto the protostars, less feedback from the bottom. And so we get into a nicely self-regulated state. But the key thing is that if I now use the same calculation, but I take away the magnetic field, I only have these protostellar jets, right, all these outflows, what will happen is that again, the material just goes into a runaway. It just flies out. And that's because the protostellar jets, even though they put in this momentum, they can share it with enough material. What they do is they blow it out of the cloud, and it's like, I sort of think of like I have a water hose or something, and if I blow it out the window, well, it's out the window, right? But if first interacts, if I blow it on a chair before, it can spray all over the place in the room. And that's the same thing in a way. If you imagine protostellar outflow trying to get out of the cloud, whipping out the magnetic field lines with it. Well, these magnetic field lines are anchored in many different parts of the cloud, and it's phase waves now that can actually transport the momentum you inject throughout the cloud. And I think that's very crucial in regulating star formation. The important thing here is, back here is about 6 dynamical timescales. And now I had a cloud, an infrared dark cloud, sort of the model that could go and make stars for many dynamical times. And that's quite crucial because in all the other calculations you're usually shown, what happens is you have this exponential runaway. That means, the massive stars that should shut off star formation to explain the low efficiencies of having very low fraction of gas go into stars. The massive stars have to be exactly on time to disperse all the other material. Now, but in the case where it's just nicely self-regulated, get the material, whether the star now forms a little earlier or later, it'll have plenty of time to get rid of the material because star formation is regulated and slow. Anyhow, so unfortunately, it didn't leave quite enough time for the very end here. It was just a calculation in a somewhat larger cloud, where then also follow, what makes all the H2 regions. And we try to visualize this in a way that's sort of more observationally relevant, so it has the right dust correction, etc. Okay, alrighty. So what we're essentially doing now is we're putting all these things together. They have all these ingredients, magnetic fields, radiation transport, star formation, this sort of feedback, to make models of galaxy formation as realistic as we can. And so we have recent ones now with up to 350 million stellar particles in these calculations. Shameless advertising, this code, ENSO 2.0, which was used for all the calculations I showed you today, is completely publicly available. There is nothing that we keep secret, if you want. Everything's completely open source. You can use it for anything you want. There's a free BSD license. And, please feel free to use it in your own investigations and just contribute back to the code base if you'd have any. Would be great. Let me just skip that too. Just saying is, of course, when you look at individual galaxies, they're just so amazing in the detail they had. And also, if you think about how many dynamical timescales they've already lived, that, in some sense, our model is still so rudimentary, so simple compared to the real universe. But I hope you get the sense now as well that sort of over the last decade or so, we're actually getting there. It's becoming to the point where you literally can look at scales less than a parsec while looking at an entire galaxy and still evolve it for gigayears. And so it's getting there. And the beautiful thing about computational physics in general, and computational astrophysics in particular, is that as you develop these codes and these numerical techniques, you always build upon your last iteration. So it's not, you're always improving. So the models really, in that sense, only get better. So you never have to take a step back and say, oh, now let me assume something else so that I can get a closed analytic solution. You're actually just improving your capability of making predictions and understanding the universe as it is. And the one thing, if you really want to just do something challenging, please work on cosmic rays and galaxy formation. Yeah, thanks so much.
Okay, time for a few questions.
You mentioned that in the early stars there are 4 binaries or multiple systems. Do you have any hint, or have you studied in the current universe percentage of binaries or triple systems?
In some sense, actually, that fits very nicely. Massive stars in the galaxy are known to have predominantly binaries, in fact. And you also know this from multiple systems, all these runaway O stars. And so that part, whatever exactly the connection now is of how this works for massive stars, being so good in making multiple systems, we get that there too. What's remarkable, though, at least for these multiple systems that form in the initial collapse, that's the ones that we can study best. Yeah, it's actually a small fraction in our cases. We only find about 1 in 5. And that would still be different. But I think you're much more likely in the later evolution that we cannot calculate yet to make these multiple systems. Mm-hmm. For gamma ray burst folks, this is quite exciting to have multiple systems, because you have the chance of, even after a star, when it lost its hydrogen envelope, that hopefully through its companion it can be spun up again, and making the likelihood of making the gamma ray burst higher, which would be lovely, of course, if we could probe gamma ray bursts not only to redshift 8.3, but 13 or 15.
Thank you.
Hi. As you know, one of the most debate topics right now is whether the initial mass function of the stars are universal or not. Maybe it's not directly related to what you are doing, but because you are treating particularly or mainly the initial universe. But according to your simulation, what would you expect? So do you expect some kind of universality, or do you expect changes from galaxy to galaxy?
So, great question, of course. But it's all beautifully. It's always one of the hardest ones as well. Just even observationally alone, it's already amazing. The level of detail we have to understand of being able to understand all the errors just enough to see the differences. What I can say is, for the calculations I showed you with the proto-stellar outflows, I designed a model, a sort of a subgrid physics model, that in fact gets exactly the IMF correct to the level of what is observed. And so here, what I show you is actually the IMF. The black line was for hydro models that only had hydro, no magnetic fields and no winds. And that's the one I sort of tuned it with. I just, in the numerical model, I'm saying, look, I'm only going to 200 AU resolution. Much of the physics that will set the final mass of these stars, or whether they multiples, that will all much of that will still happen yet on smaller scales. So I say I design the algorithm such that I get the right answer, because I wanted to study what that IMF then inputs back into the cloud, right? But you could be optimistic and hope that now, if I change things in the physical model, like I include the proto-stellar winds, I include the magnetic field, that I might at least get a hint of how those physics shape the initial mass function. And this may be true, but on a mathematical level, you're not on a solid basis, because it's a very dodgy way of doing physics when you do a subgrid model. But anyhow, what we find with doing MHD plus wind calculations, that the IMF that we got shifted to lower masses. So the characteristic mass was roughly half. And in a way, I think it actually has to do with, even if you accrete along a filament, like as soon as you have a protostar, it actually sort of separates more of the material. You get about half the sort of inflow rate. So, that is already one thing, that you get about half the typical accretion rate onto the object, which already led to about getting half the solar mass. So these are the type of physics you get a hint for, but these are not solid predictions in any way, I'm afraid. And I hope our model is good enough now that I can now extrapolate to say, okay, how does star formation happen at 10 to the minus 3 solar metallicity? Not clear at all, how that works. But no.
Okay. Actually, two questions. First is, you promised talking about the role of magnetic fields in the formation of galaxies, and so it's asking you to tell us something about that, and also about the seeds for the supermassive black holes. Are these first stars, or they are made? Could you say something about these supermassive black holes?
Mm-hmm. So yeah, for the supermassive black holes, I usually have a whole hour-long colloquium that I also give on this. And the sort of main points there is that these early stars, because they're in these very special locations of very small galaxies, and they're very bright, they evaporate all the gas around them. We've done many calculations now, and if these first seed black holes, they always seem to grow very slowly. So we cannot get them to grow rapidly, and so I'm very skeptical that they are actually relevant for the formation of quasars later on. Despite lots of people were excited about this, because in principle you have more time, right? Because you make these seed black holes very early on. But in reality, I think it's actually they're in the worst places. They're in tiny little galaxies. They evaporate. You're much better off making this in situ in relatively large galaxies. Once you have a 10 to the 11 solar mass galaxy, the central region, you make enough horizons. It doesn't matter whether you had a HOP3 star 300 million years earlier or 500 million years earlier. You have no problem making a horizon in 10 million years. Just make a massive star, boom, there it is. Right? And so you can do that in situ, and it's already 100 million year time scale for the central of the galaxies. That's sort of the one. And so I think but for the magnetic fields, I think we did these experiments a couple of years ago now, which were really quite remarkable, that there's all this literature that tells you that it's very difficult to make magnetic fields, and we don't understand how the magnetic field in the Milky Way forms, and it's quite awkward. As far as I can tell, I trace this back to a simple argument where people had, where they really thought of the Milky Way having existed since the universe beginning, and then just imagine how few rotation the Milky Way had on the outskirts since then. In that picture, which is not, of course, our picture of hierarchical cosmological buildup, you'd just have two dynamical times, right? I mean, I could only do a couple of rotations, so how could I possibly build a magnetic field? we're finding from these calculations here, where we just sort of follow this galaxy for about a giga-year, and we sort of think of that as a small dwarfish galaxy that might have existed at redshift 2 or so, or a few, and would be tens of these would be the progenitors that become the Milky Way. Within a few 100 million years, it already built up to equipartition strength. The field, in that sense, has no problem. I mean, in some sense, with a small-scale dynamo, you're always building the field, always. Right? It's all there's always some small-scale vorticity that will amplify field. It's more the question of it will saturate eventually because the field starts acting back on the flow. In these numerical experiments, don't have quite fully time to explain this. We already saw that the plasma measures the gas pressure of the magnetic pressure. Okay, so gas pressure completely dominates. I mean, it feels irrelevant. It very quickly goes down, and then this part here was actually the cold phase. It actually almost goes down to a tenth, which is crazy. It's just like in the Milky Way, and we didn't mean to model the Milky Way at all. But you still get a few microgauss at these sort of tens particles per cubic centimeter already, even in a tiny little galaxy. So I think what that teaches you is that if you sort of think about the hierarchical buildup, you have so many dynamical times that it's really no problem at all to produce large magnetic fields. And for the coherence, that you get in 1 or 2 dynamical time to get a component that has a large scale coherent component to your field structure. So I think from this looks we're very optimistic, and of course it's also perfect timing now because with LOFAR and many of these new machines, we're actually probing exactly this type of field.
Okay, thank you.
Okay. I may have a related question to one of the previous questions, talking on IMF of stars. So you think there is a slope, there is a lower mass limit, higher mass limit. Who gives that? Or how is that given, the upper mass limit? Who says that this is 300 solar masses or so? Yeah,
so for that one, so there's different opinions on this. And in some sense, it'll be a very statistical driven thing too, like, because, like all the things, we always have some tail. So it'd be hard to answer any of that. The 300 solar masses I got is because for the typical accretion rates that I find in my calculations, it looked like it would have to accrete longer than the lifetime of a 300 solar mass object in order to get above 300 solar masses. And so it now depends though on the mass, because if it's 260 solar masses, it actually would go parent-stability. It could explode, and then it's likely over with the star. But unfortunately, it's not that even our stellar evolution calculations are not predictive enough to inform exactly this. Even in the most idealized case of a spherical model, we cannot quite predict actually the final mass. There's a longer answer too, but today and tomorrow. Yeah. Okay. Thanks.